Alright, we're going to talk about isomers, structural isomerism. Isomers have the same molecular formula, but they can have different structural formulas. For example, both N-butane and 2-methylpropane have the formula C4H10, but they have very different structures, okay, and different physical and chemical properties. Okay. Then you have 1-butene, 2-butene, and methylpropene. All have the formula 6,4H8, but all have different structures. We're going to talk a little bit more about these differences and the effect they have. So, structural isomers have the same molecular formula, but different structural formulas. But then we have stereoisomers. They have the same structural formula, but they differ in their spatial arrangement. What this really means is they're going to look the same when we draw them, or can look the same when we draw them in 2 dimensions, but they're going to differ in the 3-dimensional space. And we have 2 categories of stereoisomers, geometrical and optical isomers. For geometrical, it occurs when a movement about a bond is restricted or prevented. If you remember, if you have just a single bond between 2 atoms, they can rotate about that bond. Okay, and they do. They rotate about the bond. They move this way, and there's vibrational motion in there. Right, so if I have a double bond, remember I have a pi bond, and that pi bond is over the p orbital. Okay, so each of these, you have this is really the pi bond, as opposed to the sigma that is in line with the 2 atoms, and this restricts the motion around that bond. So if I have the cis isomer, okay, I have 2 things on the kind of the same side, right? Trans, I'm going to have them on opposite sides. Okay, and they're fixed in that position, and it does help to actually make these things in 3 dimension. Okay, you can also have di-substituted cycloalkanes, meaning cyclo meaning they're in a circle. Cyclopropane, it is fairly reactive because it's not very stable with the density of the electron cloud. But you see I have these 2 chlorine atoms on the same side, cis, or I can have the chlorines on opposite side with the trans form of the 1,2-dichlorocyclopropane. And we should add this cis and trans when we're talking about alkenes or a cycloalkane that has 2 substituted groups on them. Okay. The cis and trans have different physical properties, and it has to do with the intermolecular forces between these molecules, dipoles and van der Waals. The trans form, with those identical groups on either side, the dipole moment is actually canceled out, so this is more likely to be nonpolar. With the cis being on the same side, those dipole moments or those unequal sharing don't cancel each other out, and they tend to be polar. So there is a difference sometimes in both physical and chemical properties. And we're going to take a minute and look at the cis and trans forms of 2-butene 1,4-dioic acid. Here is the trans form, and here is the cis form. What we're showing here is that carboxylic group and this OH group can be attracted via a hydrogen bonding, okay, and eventually form a cyclic compound. Okay. Whereas in the trans form, these 2 groups really don't get close to each other in order to form that attraction and do that condensation reaction. Okay, so optical isomerism, shown by all compounds containing at least one asymmetric or chiral carbon atom. This is a carbon atom that has 4 different groupings attached to it. The 2 isomers are known as enantiomers, and they are mirror images. You cannot place them over each other. The difficulty is identifying these working in a 2-dimensional space as opposed to a 3-dimensional. Okay, these enantiomers are optically active with plane polarized light. Okay, so they both rotate plane polarized light. Normal light consists of electromagnetic radiation in all of the planes. Okay, and when they pass through a polarizing filter, the transmitted rays only vibrate in one plane, and then that light is said to be plane polarized. So we have light going through a polarizer, one plane, and it goes through the sample. The enantiomer is going to rotate the light in one direction, okay, by certain degrees. And then you can pick that up with a detector, right? This is called a polarimeter. And this is a little better picture of it. Okay. Here's the tube with the sample in it, and you can see that from the light source, many different rays coming out, lined up in one plane, coming through the sample. It rotates it a certain amount. All right. If it's rotated clockwise, it is said to be dextrorotatory. Jeez. From the Latin dexter, meaning right. And then if it rotates it the other way, it's meaning left. Not even going to try. One form is known as the D, so if it rotates it to the right, it's known as the D form. The other is known as the L form. When we have both of the stereo optical isomers in a mixture, it is known as a racemic mixture. And I don't know if I'm saying that right either. Jeez. So the amount of this rotation depends on, 1, the length of the sample tube, and the concentration of the enantiomers, and that makes sense. Right, and if they're both present, that rotation cancels out and there'll be no net rotation. Interesting thing about enantiomers, depending on whether you have the L or the D form, for this particular, the amino acid, one can taste bitter, the other one tastes sweet. Sometimes these have catastrophic results depending on which optical isomer is present. There's a drug called thalidomide, and you can search that online and search for images. One enantiomer combated morning sickness. It was taken in the 50s for morning sickness. The problem was the other enantiomer made or was responsible for fetal abnormalities. So the sad part is you're taking a medication for morning sickness, but that medication also consisted of some of its other optical isomer that caused fetal abnormalities. Okay. So it was released in 1958. Severe adverse side effects began to appear in 1959. The company released the drug even though some trials indicated some problems as early as 1956, and it was taken off the market in 1961. It's coming back for some types of cancers and also for leprosy, and I'm sure that they have strict controls on it to make sure that pregnant women don't take it. And that ends the discussion of isomers.